perfectly balanced if one of the most famous unsolved problems in all of mathematics. A paper drops in June 2026, claiming to have built a mathematical machine that can only stay perfectly balanced if one of the most famous unsolved problems in all of mathematics is actually true. Welcome to Copilot Podcasts. Today, we are diving into the full structural proof summary of the Riemann hypothesis, specifically what the Riemann hypothesis actually says, how a brand new kernel lattice framework turns it into a symmetry problem, and why 4 interlocking constraints are the secret engine of the whole argument. By the end of this episode, you will understand the core logic of this approach well enough to explain it to someone else. I've got someone here who has gone deep into this paper, so let's get into it. Walk me through what we are actually dealing with.
So the Riemann hypothesis, RH for short, was proposed by Bernhard Riemann back in 1859. And the statement itself is deceptively simple. It says that all non-trivial zeros of the Riemann zeta function lie on a specific vertical line in the complex plane, the line where the real part equals 1/2. That line is called the critical line.
And when you say zeros, you mean the inputs that make the function output 0?
Exactly. The zeta function takes complex number inputs and spits out complex number outputs. There are some obvious zeros, the negative even integers, those are called trivial zeros. But then there are these other zeros, the non-trivial ones, and they all appear to sit on that critical line at real part 1/2. The hypothesis says that's not a coincidence. It's a structural fact.
And this matters because of prime numbers, right?
Deeply. The zeta function is connected to the distribution of prime numbers through what's called an explicit formula. The location of those non-trivial zeros directly controls how primes are spread out across the number line. So RH is not just abstract, it has real consequences for number theory, cryptography, and computational mathematics.
And according to a 2026 survey cited on Wikipedia, there is overwhelming numerical evidence for the hypothesis, but no proof. So we've checked billions of zeros and they all sit on that line, but nobody has proven it has to be that way.
Right. Numerical verification is not a proof. You could check 1 trillion zeros and still not rule out that the trillion and first one sits somewhere else. That's the gap this paper is trying to close.
So tell me about the paper itself. Who wrote it and where was it published?
The paper is by Shaima Saeed Sultan, published in the Journal of Mathematics Research, Volume 18, Number 2, June 2026. The DI is 105539 EJMR.V18N2P45. The title is A Kernel Lattice Criterion Equivalent to the Riemann Hypothesis. And the core claim is that the author has developed a framework that produces a criterion, a test, that is logically equivalent to RH.
Equivalent meaning, if the criterion holds, RH is true, and if RH is true, the criterion holds?
Exactly. It's a two-way street. The paper doesn't just say, here's a consequence of RH. It says, here is a condition that is true if and only if RH is true. That's a much stronger claim.
Okay, so before we get into the machinery, the paper introduces this concept of a pure non-trivial zero. What is that?
So the paper starts by classifying functions. You have purely even functions, purely odd functions, and then what the paper calls the mixed class, functions that are a combination of both. The zeta function lives in that mixed class. And a pure non-trivial zero, or PNTZ, is defined as a point of perfect equilibrium, a state where the even energy and the odd energy of the system exactly cancel each other out. The paper calls this the cancellation principle, or the lock state.
So a zero isn't just where the function hits 0, it's where 2 opposing forces are in perfect balance.
That's the framing, yes. And the paper makes a strong structural claim from this. Non-trivial zeros are a unique phenomenon of the mixed class and are structurally impossible in any other functional category. Pure even or pure odd functions simply cannot generate this kind of cancellation state.
That's a really elegant way to think about it. It's not just a location, it's a type of event.
And that framing sets up everything that follows. Because once you understand zeros as equilibrium states between even and odd components, you can ask, what structural conditions force that equilibrium to happen only on the critical line?
Which is exactly what the rest of the paper answers.
Right. And the answer comes in 4 parts. The paper calls them 4 interlocking constraints: harmonic reduction, even-odd cancellation, normalization completeness, and zeta symmetry. The structural conclusion of the paper is that these 4 conditions together force every non-trivial zero to lie on the critical line. And crucially, if you remove any single one of them, the whole cancellation structure collapses.
Okay, let's slow down on each of those. Harmonic reduction, what does that mean in this context?
Harmonic reduction means that the oscillatory remainder term in the explicit formula, the part that's left over after you account for the zeros, is forced into a very specific form. It has to satisfy a second-order harmonic equation, which means its solutions are uniquely the trigonometric pair cosine and sin. There's no other independent oscillatory basis. The paper proves this formally as Theorem 12.
So the math is saying the only oscillations allowed in this system are sin and cosin, nothing more exotic.
Exactly. And that constraint is powerful because it limits what the remainder can look like. Once you know the remainder is built from cosine and sine, you can analyze its even and odd parts very precisely.
Which brings us to even-odd cancellation.
Yes, the paper decomposes the remainder into its even part and its odd part, and it shows that for a zero to exist, for that lock state to happen, the integrated odd contribution has to exactly cancel the even boundary value. The paper expresses this through what it calls the dual cancellation functional, and this cancellation can only happen within a specific height range.
And the third constraint, normalization completeness, pins down where that range is?
Precisely. The normalization completeness theorem, which is Theorem 2 in the paper, says that every admissible cancellation event can be represented within the normalized height window from 0 to 1. No additional cancellation mechanisms exist outside that interval. So the window is complete. You don't need to look anywhere else.
And then zeta symmetry, the functional equation, fixes the midpoint.
That's the fourth constraint. The completed zeta function satisfies the functional equation xi of s equals xi of 1 minus s. That symmetry maps the interval 0 to 1 onto itself, and the only interior point fixed by that reflection is the midpoint, s equals 1/2. So, when you combine all four constraints, harmonic reduction, even-odd cancellation, normalization completeness, and zeta symmetry, the only height compatible with all of them simultaneously is the midpoint, which corresponds to the critical line.
That is genuinely beautiful. 4 independent constraints, each doing a different job, and they all point to the same place.
And the paper is explicit that this is not a coincidence. It says, and I'm quoting directly from the structural conclusion, if any one of these 4 requirements is removed, the symmetry of the zeta function is violated and the cancellation structure collapses. They all have to operate simultaneously.
Now let's talk about the actual kernel, because this is where the paper gets really technical. What is the kernel K of X?
So the kernel is the central analytic object in the paper. It's written as K of X equals cot of X times cot of A times 1 minus X times a normalization function na of X defined on the open interval 0 to 1. The cotangent factors are what give the kernel its oscillatory structure and its reflection symmetry. The normalization function na is chosen to enforce evenness and lattice calibrating.
And the paper says this kernel is not arbitrary, it's actually derived from the functional equation of the zeta function itself.
That's a key point. The paper says the kernel is the continuum analog of what it calls the normalization gear of the zeta functional equation. It's designed so that the kernel lattice decomposition reproduces the same symmetry constraints that govern the analytic behavior of the zeta function. So the kernel is not invented out of thin air, it's extracted from the structure of the problem.
And then you evaluate this kernel on a lattice, a discrete set of sampling points.
Right. The lattice is defined as the set of points x equals n plus r divided by 2a, where n ranges over all integers and r is in the interval 0 to 1. The parameter a controls the sampling density. And a crucial feature is that the midpoint x equals 1/2 is a fixed point of the kernel for every value of a. The paper calls this the locking mechanism. The kernel is locked at the symmetry point regardless of the scale.
So the midpoint is not imposed from outside, it emerges from the interaction of the kernel and the lattice.
Exactly. The paper is very careful about this. It says the midpoint is not imposed externally, it is the unique location where the symmetry of the kernel and the sampling structure are simultaneously respected. That's a structural fact, not an assumption.
Now here's what I want to understand. How does this kernel actually connect to the zeros of the zeta function?
Through what the paper calls the explicit formula. You insert the kernel into a contour integral involving the logarithmic derivative of the completed zeta function, that's xi prime over xi. When you shift the contour, you pick up residues at the poles, which are exactly the non-trivial zeros of the zeta function, the trivial zeros, and the poles at 0 and 1. The result is a decomposition. The transform aa of x equals a zero sum plus a remainder term na a of x.
And the remainder is the key?
The remainder is everything. The paper shows that the remainder na of x decomposes into an even part and an odd part. And the central claim, Theorem 6, the parity equivalence theorem, is that the following 5 statements are all equivalent to each other. The functional symmetry of the completed zeta function holds. The full transform aa of x is even. The remainder na of x is even. The odd companion vanishes. And all non-trivial zeros lie on the critical line.
Wait, so the Riemann hypothesis is equivalent to the odd part of the remainder being 0?
That's the punchline. The paper calls the odd part the odd companion, and it's defined as 1/2 times na of x minus na of 1 minus x. If that quantity vanishes identically on the sampling lattice, RH is true. If any zero sits off the critical line, that odd companion is non-zero. And the paper proves that a non-zero odd companion cannot be cancelled. It's structurally impossible.
Why can't it be cancelled?
Because of what the paper calls the irrational frequency obstruction. If a zero has real part different from 1/2, say it's 1/2 plus beta, where beta is non-zero, then its contribution to the zero sum oscillates with a frequency of 1/2 plus beta divided by 2a. For almost all values of the parameter a, that frequency is irrational. And an irrational frequency oscillation cannot vanish identically on the integer lattice. It just keeps oscillating. There's no way to cancel it with the even remainder, which only contains rational frequencies.
So an offline zero would leave a fingerprint, an oscillation that can never be erased.
That's exactly the contradiction mechanism. The paper lays it out in section 8.5 as a 5-step argument. The odd part of the kernel vanishes on the lattice. The remainder is even, so it contributes no odd part. Therefore, the odd part of the zero sum must vanish on the lattice. Any offline zero produces an irrational frequency odd oscillation. Such an oscillation cannot vanish identically. Contradiction, unless all zeros lie on the critical line.
That's a remarkably clean logical chain.
And the paper backs it up numerically. There's a worked example using the first non-trivial zero of the zeta function, which has imaginary part approximately 141347. The paper computes the lattice parameter a1 corresponding to that zero. It comes out to approximately 05897, and then shows that the kernel expression evaluates to essentially 0 at x equals 1/2 and is non-zero everywhere else in the interval. The numerical output is in the paper. At x equals 0.5, the kernel value is negative 1.776 times 10 to the minus 15. Machine precision 0.
So the locking is not just theoretical, you can actually see it in the numbers.
You can see it very clearly. And the paper also demonstrates the reverse direction. Given the imaginary part of a zeta 0, you can solve for the lattice parameter a that reproduces it. The equation is a one-to-one correspondence between zeta zeros and lattice parameters. The paper calls this the bijection between the set of ordinates and the set of admissible parameters.
I want to flag something here because I think it's important for listeners. The paper is published in a peer-reviewed journal, but that doesn't automatically mean the mathematical community has accepted it as a complete proof of RH. These things take time to verify. What's the honest framing here?
That's the right question to ask. The paper presents a criterion equivalent to RH. It establishes a logical equivalence. Whether every step of the argument is airtight is something the broader mathematical community will scrutinize carefully. The history of RH is littered with claimed proofs that didn't survive peer scrutiny, including a high-profile attempt by Sir Michael Atiyah in 2018 that was ultimately not accepted. So the honest framing is, this is a serious, published, structured argument that deserves careful examination, not a declaration that RH is solved.
And the Clay Mathematic Institute, which offers $1 million for a solution, has its own verification process that's entirely separate from journal publication.
Correct. The prize requires the solution to be published in a reputable journal and then withstand 2 years of scrutiny from the mathematical community before the prize committee even considers it. So publication is step 1 of a much longer process.
What makes this approach structurally different from previous attempts? Because there have been a lot of them.
Most previous approaches try to directly analyze the zeros, their density, their distribution, their correlation with random matrix theory. This paper takes a different angle. It doesn't try to locate the zeros. Instead, it builds a probe, the kernel, that is calibrated to be perfectly symmetric, and then asks, what does the explicit formula look like when you evaluate this probe on a lattice? The answer is that the probe can only stay balanced if all zeros are on the critical line. It's indirect, but structurally very clean.
It's like designing a scale that tips the moment anything is out of place, rather than trying to weigh each item individually.
That's a good analogy. And the paper is explicit that the kernel is a probe of the spectrum, not a mapping of the complex plane. Scaling the normalization function doesn't move zeros, it just changes how their contributions are combined. The zeros are always the actual zeros of the zeta function. The kernel only controls how their contributions interact.
The paper also talks about the Mellin transform playing a specific role. What's that about?
The Mellin transform acts as what the paper calls the symmetry lock transfer gate. The midpoint symmetry of the kernel in X space, Ka of 1 minus X equals Ka of X, gets transferred through the Mellin transform into a functional equation in S space, Ka of 1 minus S equals negative Ka of S. The paper says Mellin guarantees the bidirectional transfer of symmetry and locking. So the symmetry in the real variable X and the symmetry in the complex variable S are two faces of the same structural fact.
And the paper shows this extends beyond the Riemann zeta function.
That's one of the most interesting parts of the conclusion. Section 12 outlines generalizations. The kernel lattice method is not tied to a specific kernel, a specific odd companion, a specific lattice, or even the Riemann zeta function. It extends naturally to Dirichlet L functions, modular L functions, and general automorphic L functions, any L function that satisfies a functional equation of the right form and has an explicit formula. So if the approach holds up, it's not just a proof of one conjecture, it's a framework.
That's a significant claim. You're saying the same structural logic could potentially apply to a whole family of unsolved problems in analytic number theory.
That's what the paper suggests. The essential structure, functional equation symmetry in the kernel, an odd companion isolating the odd spectral component, an even remainder in the explicit formula, lattice calibration forcing the odd part to vanish, and an irrational frequency contradiction for offline zeros, that structure is described as universal and adaptable to a wide range of analytic settings.
Let me ask you something that I think a lot of listeners will be wondering. The paper uses a lot of machinery, cotangent kernels, Mellin transforms, Schwartz functions, contour integrals. Is there a way to state the core insight in plain language?
I think so. Here's the core insight. The zeta function has a deep symmetry, its functional equation. That symmetry forces the function to be balanced in a very specific way. The paper builds a mathematical probe that is calibrated to respect that same symmetry. When you use the probe to sample the zeta function on a discrete lattice, the probe can only stay perfectly balanced, locked at the symmetry point, if every zero of the zeta function sits exactly on the critical line. Any zero that wanders off the line creates an imbalance that propagates through the system as an oscillation with an irrational frequency. And irrational frequency oscillations cannot cancel. So the imbalance is permanent and detectable. That's the contradiction.
So the proof is essentially saying the symmetry of the zeta function is so rigid that there is literally no room for a zero to be anywhere other than the critical line.
That's the structural claim. And the paper frames it beautifully in the conclusion. It says, the Riemann hypothesis is not merely a statement about the distribution of primes, but a structural consequence of four interlocking constraints governing the zero axis. The word consequence is doing a lot of work there. It's saying RH is not a coincidence. It's forced.
Okay, so when you step back from all of this, the kernel, the lattice, the four constraints, the irrational frequency contradiction, what does this really come down to?
It comes down to parity, even and odd. The zeta function's functional equation enforces a symmetry. The kernel is built to respect that symmetry. The explicit formula transmits the influence of the zeros, and the odd projection of the remainder is the single quantity that captures everything, whether any zero is off the critical line. If that odd projection is zero, RH is true. If it's non-zero, RH is false. The entire 105-page paper is a rigorous argument that the odd projection must be zero.
And the paper establishes that equivalence in both directions. Not just that RH implies the odd projection vanishes, but that the vanishing of the odd projection implies RH.
Both directions. That's Theorem 9, the kernel lattice equivalence to the Riemann hypothesis. The forward direction follows from the explicit formula under RH. The reverse direction uses the irrational frequency argument to show that any offline zero would produce a non-vanishing odd oscillation, contradicting the lattice identity. So the equivalence is complete.
Here's what I find genuinely thought-provoking about this. The Riemann hypothesis has been open for 167 years. Mathematicians have thrown spectral methods, random matrix theory, algebraic geometry, and quantum chaos at it. And this paper is saying the answer might come from something as fundamental as the balance between even and odd.
And that's not entirely surprising if you think about it. The deepest results in mathematics often turn out to be consequences of very basic structural symmetries. The functional equation of the zeta function has been known since Riemann. The even-odd decomposition of functions is undergraduate mathematics. What's new here is the specific way those tools are assembled, the kernel, the lattice, the odd companion, the irrational frequency obstruction, into a coherent argument.
The paper also acknowledges its own limitations, honestly. It says the author used AI-assisted tools for language refinement, but that all mathematical ideas, constructions, proofs, and analytic arguments are entirely the author's own.
That transparency is important. And the paper's acknowledgement section is careful to situate the work within the classical tradition, citing Riemann, Hadamard, von Mangold, and Weil as the foundational figures whose explicit formulas and structural insights the kernel lattice framework builds on. This is not presented as coming out of nowhere.
So here's the bottom line for our listeners. A paper published in a peer-reviewed journal in June 2026 presents a new structural approach to the Riemann hypothesis. It builds a cotangent-based kernel that mirrors the functional equation of the zeta function, evaluates it on a discrete lattice, and shows that the odd projection of the Riemann term vanishes if and only if RH is true. The core argument is that any offline zero would produce an irrational frequency oscillation that cannot be cancelled, a permanent, detectable imbalance. And the framework is designed to extend to a whole family of L functions beyond the Riemann zeta function.
That's the summary. And the honest caveat is that the mathematical community will need time to verify every step. But the structural logic is transparent, the argument is non-circular, the paper is explicit about that, and the numerical examples check out. It's a serious piece of work.
Here's the thing that lingers for me. The paper says that if you remove any one of those 4 constraints, harmonic reduction, even-odd cancellation, normalization completeness, zeta symmetry, the whole structure collapses. That means RH is not just true in isolation. It's true because of a web of interlocking necessities. And that's a very different kind of truth than we checked a trillion zeros and they all lined up.
That's the deepest point. Numerical evidence tells you what is happening. A structural proof tells you why it has to happen. And if this argument holds, the answer to why is because the symmetry of the zeta function, the harmonic nature of its oscillations, the completeness of the normalization window, and the reflection symmetry of the functional equation all conspire together to leave the critical line as the only possible home for a non-trivial zero.
Math's hardest open problem, potentially cracked by asking, what happens when even and odd can't stay in balance? That's a sentence I did not expect to say today. Thanks for walking us through this genuinely fascinating stuff. And to everyone listening, the next time someone tells you the Riemann hypothesis is just about where some zeros happen to land, you can tell them it might actually be about something much more fundamental, the structural impossibility of imbalance. That's it for today's episode of Copilot Podcasts. Stay curious.